Hello students, I hope in the previous topic we have discussed the principle of capacitor, and that must be crystal clear in your mind, isn't it? The concepts must be very clear. So what we have discussed was a capacitor is an arrangement which is capable of storing a huge amount of charge. And what was that arrangement? An earth connected uncharged conductor placed near a charged conductor, right? That was the arrangement we were discussing. That forms a capacitor. Now in this section we will discuss parallel plate capacitor and the expression for its capacitance. Now look, there can be various types of capacitors, like if the two conductors under consideration are in the form of parallel plates, one charged, the other one uncharged, then the combination is said to be parallel plate capacitor, right? If the two conductors happens to be in the form of concentric spherical shells, then that capacitor would be known as a spherical capacitor. Another scenario we can consider the case of conductors in the form of coaxial cylindrical shells. In such a case, the capacitor would be known as cylindrical capacitor. So basically what I intend to say is that there are parallel plate capacitor, spherical capacitor as well as cylindrical capacitor. And we have discussed the capacitance does depend upon the shape and size of the capacitor. That is, it depends upon the dimensions. So it is but obvious the expression for the capacitance for different types of capacitors would be different. So let's start with parallel plate capacitor. And as I have told you, parallel plate capacitor will contain two parallel sheets of negligible thickness. These are the two parallel sheets. Suppose this is the first one, this is the second one. Remember, of negligible thickness, right? So these are the two parallel sheets, while d be the distance between them. Suppose the space between them is filled with air or it is vacuum. Now this is the charged conductor, this one must be earth connected uncharged conductor, right? It must be earth connected uncharged conductor, like this. It is to be given positive charge. And suppose both the plates are of area A. So these are the two plates, identical, each of area A, right? Having negligible thickness. We have considered the area to be A and the separation between them is considered to be small d. So this is the charged one. This is the uncharged one, uncharged conductor. So what happens is, on its inner face negative charge will be developed. On its farther face positive charge will get developed, but due to earthing that positive charge will get neutralized. So this is the diagram. So if it is having charge of plus q, it will be having net charge of minus q. Surface charge density, you are aware, it's charge per unit area, isn't it? So if it is having positive charge density, it will be having equal negative charge density. Remember this case, we have done it in the applications of Gauss theorem due to two infinitely thin parallel plane sheets of charge, right? So we will be making use of that result only, right? So what we discussed there was, in the extreme region, the electric field is 0. Agreed now? These are the extreme region. Here, the electric field is 0. Here also, the electric field is 0. And at a point in the space between these two plates, the electric field is given by sigma by epsilon. Students, do you remember this? This article we have done in the section of applications of Gauss theorem, right? Do remember this. Okay, again I will tell you. Due to a plane sheet of negligible thickness, the electric field at a point is given by sigma by 2 epsilon. This is positive charge plate. So due to this, the electric field at this point would be along this direction, E1. It would be equal to sigma by 2 epsilon. Negative charge. Due to this negative charge, the electric field would be towards the negative charge. Again, magnitude would be same. It would be again sigma by 2 epsilon. So what would be the net electric field inside the space between the two plates? It would be equal to E1 plus E2, and that would be sigma by 2 epsilon plus sigma by 2 epsilon. So that will give us sigma by epsilon. That's the net electric field in this space between the two parallel plates, right? You can write it directly or you can simply derive it like this. So that's electric field. And sigma, that's surface charge density, that is charge per unit area, isn't it? So charge Q per unit area of each plate is considered to be A. Right? Put this as equation 1. Now, in order to find out the capacitance, the master formula is C equals to Q by V. So, we need to find out the potential difference between these two plates, right? So, knowing the value of potential difference and substituting the value in the formula C equals to Q by V, we can easily find out the expression for the capacitance. So, what to do is, since we are aware of the electric field, so potential can be determined, and it can be determined by the formula E in magnitude. You are aware, it's given by dV by dr in magnitude. Again, we have done this. I have told you numerous times. If the potential is given, the electric field can be found, and vice versa by using this relation. So the potential difference is to be determined. So potential difference between these two plates, suppose it is V be the potential difference. V1 minus V2, suppose it is V. On integrating and taking suitable limits, we will get potential difference V1 minus V2, that is considered to be V. It is E. Electric field at any point inside the space between the two parallel plates may be considered to be constant, that is uniform, represented by a set of equidistant parallel lines, isn't it? So E is constant and it can be taken outside. Integration of dr from here till here, integration dr, that is from 0 to d, these will be the limits, so it will give us d. So for uniform electric field, directly you can make use of this formula. For uniform electric field, directly the potential difference is equal to the strength of the electric field multiplied by the distance between the two plates, right? So what you get is Q divided by epsilon A from equation 1 into D. As capacitance of any capacitor is given by Q by V. Therefore, substitute this value of V over here, Q get cancelled. What you get is epsilon A divided by D. This is the formula for the capacitance in the case of air or vacuum. Let us denote it by C0. C0 denotes the space between the plates is filled with air or vacuum. So students, this is the formula for the capacitance of a parallel plate capacitor. And you can see it depends upon the dimensions of the plates, isn't it? It is directly proportional to the cross-section area and it is inversely proportional to the separation between those two parallel plates. So it does depend upon the shape, size, that is the dimensions of the conductor, right? This is a special case. Suppose the medium, that is the space between the two plates, is filled with some medium, say of dielectric constant K. So the formula would become, in that case, if any medium is inserted in the space between the plates of the capacitor, then the formula for the capacitance would become epsilon A by 2. These two terms will remain constant. Only thing to be done is that in place of epsilon naught, which is the absolute permittivity of free space, we will replace it by epsilon, which will be the absolute permittivity of the medium under consideration, right? And we are aware dielectric constant or relative permittivity, it is given by epsilon divided by epsilon. Therefore, it can be written in this manner, and hence capacitance of the parallel plate capacitor, in case the space between them is filled with some medium having dielectric constant K, would be given by K epsilon A by D. Or let's compare these two. What you get is K C naught. Now I have told you in the earlier section, epsilon naught, it is the absolute permittivity of free space, 8.854 into 10 to the minus 12 Coulomb square per Newton per meter square. It's the minimum value, right? For any medium, the permittivity value is more than that of the value of permittivity in air or vacuum. So what I mean to say is that epsilon is always greater than epsilon. That is, epsilon over epsilon is greater than 1 or k is greater than 1. For any medium, the value of k is greater than 1. Therefore, we conclude that C medium is greater than C naught. That is, the capacitance of a capacitor increases when the space between the two plates is replaced by some medium. Its capacitance becomes K times. So these are the two factors on which the capacitance depends. It depends upon the nature of the medium in which the two plates are placed. Right? It depends upon the nature of the medium in which the two plates are placed, and also it depends upon the dimensions of the conductor. So this is the formula for the capacitance of a parallel plate capacitor. Now we will proceed in a similar manner in case of a spherical capacitor. Now students, you must remember spherical capacitor. It means that it will be a combination which will consist of two concentric spherical shells. Spherical shells means hollow sphere, right? So again, it will be dependent upon the dimensions. So we'll try to find an expression for the capacitance of a spherical capacitor. So let's deal with this particular case. Spherical capacitor. So as I told you, it is a capacitor consisting of two concentric spherical shells like this. This is the first shell, say of radius A, and this is the second one. Concentric means both having the common center. This is the second shell. This is the first conductor, charged one. This is the uncharged earth connected one. Let us consider its radius to be D. Right? So, this is the first charged conductor. Let plus Q charge be given over here. This is a shell. Charge will reside on its surface. It's a hollow sphere. Negative charge will get induced on an inner face of the second spherical shell. And positive charge will induce on its farther face. Will get developed on the outer face. If this uncharged conductor is earthed, then the positive charge developed on its outer face will get neutralized. So, are you able to recall the principle of a capacitor? That is, when an earth connected uncharged conductor is placed near a charged conductor, then the potential of this charged conductor decreases drastically, and accordingly the capacitance of the combination increases tremendously. So that's the principle. So this is the diagram of a spherical capacitor. Now let's try to find its capacitance. We are aware capacitance of any capacitor, be it parallel plate, spherical capacitor, or spherical conductor, or cylindrical capacitor, it's given by Q by V. In order to find the value of potential difference between these two shells, we need to find out the electric field at a point, right? And as I told you, electric field in magnitude, it's given by dV by dr. We all are aware of it. Also, dV may be written as E dr. Right? Now, in the earlier case, in the case of parallel plate capacitor, the electric field in the space within the two plates was considered to be uniform, given by a set of equidistant parallel lines. But here, the electric field in the space would be somewhat like this. It will be in the radially outward direction. They are not parallel. They are not parallel. They are in the radially outward direction. So the electric field is not uniform. It's in the radially outward direction. So electric field in this space between the two shells is not uniform. So while integrating, we can't take it outside the integration. So what we'll do is, we'll consider point D over here. Let us consider the distance of this observation point from the center of the spherical shell be R, and let us consider a Gaussian surface. Obviously, it will be a spherical Gaussian surface. Right? Now, potential difference would be given by integration of E dr. and obviously limits would be from A to B. Now E is the electric field at point P, and since electric field in this space between the two spherical shells is not constant, therefore it can't be taken outside the integration, right? So what we do is we can consider the point P to be lying outside this charged spherical shell, and as you are very much aware, whenever an observation point lies outside a uniformly charged spherical shell, then the entire charge may be assumed to be concentrated at its center. Again, this was the application of Gauss theorem due to a uniformly charged spherical shell. So again, in this article also I am making use of the result which we have derived in the earlier section. So the point to be noted is that this point lies outside this uniformly charged spherical shell. So at this point the electric field can be considered to be due to this point charge. That is, the charge which otherwise was distributed uniformly over its surface may be considered to be concentrated at its center. So what is the electric field at point P due to this charge? That is K 1 over 4 pi epsilon Q by R square dr. Limits will be from A to B. Understood? So the constant term can be taken outside. It will be Q over 4 pi epsilon 1 by R square dr. Limits are from A to B. Integration of 1 by R square is minus 1 by R. So what we get is Q over 4 pi epsilon minus 1 by R. Upper limit minus lower limit. In order to compensate for this negative sign, I will interchange the terms. So what I get is potential. It is equal to Q over 4 pi epsilon 1 by A minus 1 by B. That is Q over 4 pi epsilon, LCM would be AB and over here B minus A. Put this as equation number 2. So that is how the potential difference between these two shells can be easily found. Now the last step is to substitute this value of potential difference over here. So therefore, capacitance would be Q by V. Substitute this value of V over here. So Q get cancelled. So what you get is 4 pi epsilon AB divided by B minus A. This is the formula for the capacitance of a spherical capacitor when the space between the two shells is filled with air or vacuum. Right? This is the formula. Again, look students, it does depend upon the dimensions of the spherical shells, that is radius. Right? So it does depend upon the dimensions of the conductor under consideration. In case the space between this is filled with some medium, then epsilon will be replaced by epsilon, which in turn may be written as K epsilon. So let's discuss special case. In case of a medium, C medium, it will be given by 4 pi epsilon AB divided by B minus A. So it may also be written as 4 pi epsilon K AB divided by B minus A. Compare these two. What do you get? C medium is equal to K times C naught. Since dielectric constant of any medium is greater than 1, therefore implies that C medium is greater than C naught. So what we have concluded is, be it a parallel plate capacitor or a spherical capacitor, in either case, whenever the space is filled with some medium, the net capacitance tends to increase. The net capacitance tends to increase, right? There is another very important case. So let's discuss that as well. Suppose what we consider is the outer shell. Its radius keeps on increasing. Its radius keeps on increasing. Its radius keeps on increasing. So, special case 2 is when B approaches to infinity. Let's see what happens. The case which we are discussing is that when the outer shell, the radius of the outer shell of a spherical capacitor gradually is increased and eventually and ultimately when it becomes infinite, then what will be the capacitance? So you can check it over here. So it can be written as C naught 4 pi epsilon AB B minus A. Now, just make use of your common sense and conclude what will be the scenario when the radius of the outer shell is increased gradually and eventually when the radius of the outer shell becomes infinite. So, what to do is, just like we have discussed, the potential is given by Q over 4 pi epsilon 1 by A minus 1 by B. As B approaches to infinity, here if you substitute as infinity, 1 by infinity will become 0. So V in that case would be equal to Q over 4 pi epsilon A. And C being equal to Q by V, you can substitute the value of V over here. So we get 4 pi epsilon A. So, in case B approaches to infinity, the capacitance of the capacitor would be given by 4 pi epsilon A. A is the size or rather the radius of the inner spherical shell. Students, are you able to conclude something very important thing? We have discussed for a spherical solid conductor of radius r, the formula is 4 pi epsilon r. And in the case of spherical shell also, we are getting the same formula, right? So the conclusion is, whether it is the case of a solid sphere or a spherical shell, both of same dimensions, the capacitance would be same. I repeat, the capacitance of a spherical shell or a solid spherical conductor of same dimensions are equal, each given by 4 pi epsilon multiplied by radius. So obviously spherical capacitor is preferable, right? So that's it for today's session. We'll continue in the next episode.